Welcome back to our second class. And on our last class, we talked about neural networks and how machine learning can learn from data. So yeah, this is the second day of that series, bi-weekly. So we're just gonna move on. This is basically the timeline, right? We started January 17. Today we're gonna talk about convolutional neural networks, or computer vision. I mean, like it's gonna be both. On our next class, February 14, we're gonna talk about generalization and memorization, right? As we go ahead and to train our machine learning models, how do we make sure they can convert and do well on new unseen data? And then on our last meeting, it's going to be generative AI, basically a category of AI that creates entirely new content rather than just analyzing or labeling existing data. But today, our focus is going to be on convolutional neural networks, one of my personal favorites, right? So moving on to what we will be doing today. So we have 4 chapters here, right? Chapter 1 is going to be introduction to computer vision. Chapter 2, and by the way, this is being recorded. It will also be available on YouTube for those who watch later on. Chapter 1 is introduction to computer vision and why computer vision is hard. For chapter 2, and chapter 3 is going to be the convolutional neural network, and then chapter 4 is going to be the demo. So I will do chapter 1 and chapter 2, and Alhaji is going to do chapter 3 and chapter 4. Okay, so now we're going to move on to what is computer vision. Great. So in simple terms, computer vision is basically all about teaching computers to understand images the same way we humans do, right? So now all of these examples may look very different, but I want you guys to pay close attention here. So for instance, your phone unlocking with your face, or the traffic cameras monitoring the roads, or the CT scans in the hospitals helping doctors diagnose diseases, right? I mean, like all of this at their core, they all rely on the same idea, which is basically teaching a computer how to understand visual data. Now, before like explaining further on this tree, like let's just revisit the past a little, right? So earlier approaches basically used handcrafted rules which are limited to human intervention and control. But today, deep learning basically allows models to learn these features automatically from data. So for instance, going back to the facial recognition from the phone on the first image, the system is trying to learn or is trying to recognize patterns in the human face. And on the second image, the traffic cameras is trying to learn or detect vehicles, lanes, and movements. Now, instead of a human sitting like in a room as we normally see in the old movies, like monitoring 1,000 screens, the computer does this watching for us automatically. And here's basically a simple breakdown of what you might expect happening. So first, it can basically count how many cars, trucks, or bikes are on the road to see if a street is getting too crowded. And it kind of uses digital eyes, as we may want to refer it to read license plates, or instantly for tolls or find stolen cars. And then it can notice if a car stops suddenly or if there's a crash and sends an alert to the emergency services without calling 911 or the emergency or whatsoever. And moving on to the medical imaging, like the CT scan, it all basically what it's trying to do is to learn to identify subtle patterns that the human eye might miss, right? Such as radiation, let's say in pancreatic cancer and so on. Now let's move on to the next slide. Okay. Now, basically the human system functions through a biological process, right? And what we are trying to do is to make this system, our artificial system, imitate this same process. So in the human vision system, for instance, we have like the input. So when there is sun or light whatsoever, there's going to be a reflection of the fruit in the basket, right? And that is going to enter the eye, or the eye is going to see the basket or bowl of these fruits. And then the eye, which is basically the sensing device because it has nerves attached to it, it captures the image data, much like a camera sensor will do, and it will convert this light into a neural signal. So once this is transmitted to the brain will process these complex neural signs using prior knowledge and neural networks to interpret patterns. And by the way, like the concept of neural networks, as we discussed from the last class, the inspiration is from humans, like from how the brain and nervous system works. And what happens after the brain interpret it is gonna tell you that, okay, hey, this is a bowl that contains oranges, bananas, lemons, and peaches. Now, basically, the computer system is trying to mirror the same human process, but in this case, now it's going to be a mixture of technology and algorithms, right? So we first have an input, which is going to be object or the data set or data you'll be working on, right, in front of the system. I mean, like if it's kind of hardware integrated, or a data set if you are working on like a deep learning project. And let's say you have a sensing device. So the sensing device can basically be the camera or an actual sensor, right? And what this will do is it's going to capture, scene, and convert the visual information into raw digital data. And then we have the interpretive device. So here, this can basically be the model with data has been trained on, or the computer algorithm. And basically, it's just using deep learning. It's just using deep learning models like convolutional neural networks, which we will learn more about later on, to analyze these pixel data. It then extracts these features with edges, shapes, colors, as you will see later on when Alhaji start to explain about feature extraction. And then it classifies them based on patterns learned during training. And obviously, you're also gonna have the same output from the human. That's gonna tell you that, you know what, this is whole oranges, bananas, lemons, and peaches. So in summary, like they are all trying to do the same thing. The only difference is that this is biological, created by God, and this one is an artificial one, trying to mirror or mimic what the biological output is trying to do. Now, let's move on to some deep learning architectures we have. Okay. Now, there are different architectures when it comes to this world of deep learning. And essentially, each one of them is designed for different types of problems, right? And on this slide, we basically have 5. So we'll go to some of the major like deep learning models and see what they do. But then like keep in mind, like from 2 to 5, we'll just be giving some sort of summary, because our main focus here is going to be number 1, which is like the main focus for this class. And honestly, it's basically more like the foundation for all of these other architectures. Now, first of all, the convolutional neural network, or CNN in short, like is the backbone of modern computer vision. They are especially good at working with images because they can learn spatial patterns like edges, textures, and shapes. So I keep mentioning that this is like something you will come to later on before this class ends, right? How it goes about learning these spatial patterns like edges, textures, and shapes. And for this class, like it will be our main focus because they essentially help us understand a lot of things, right? One of the things they help us understand is how images are processed. And then it helps us understand how pictures are learned, right? Alongside its main components. So you have the convolutional layers, the pooling layers, fully connected layers. And you also have, it helps us understand why deep learning works so well for vision. And as I said, once you understand CNNs, many other visions model will just start to make sense. And next is the generative adversarial networks, or the GANs. So GANs are basically like 2 networks, right? You have like, let's say 2 networks fighting each other. One is called the generator, and then one is the discriminator. Now you do not have to worry about, you will not be going further. This is the only place we're going to discuss about GANs. This is just an overview, right? It's just important to know that there are different kind of deep learning architectures. So you have a generator and a discriminator. In GANs, one tries to create a fake image, and then the other tries to detect the fakes. And what happens over time is that the fakes get so good that you can't tell them apart from real images, right? They are used for image generation, image enhancements, and even deepfakes kind of have some depicts of Obama and Queen Elizabeth, former Queen Elizabeth, the late Queen Elizabeth. When I was giving my talk on this in, I think, 2023. Yeah. So maybe if time allows at the end, I will pull them. I'm not sure if I can see them right now. So next is the variational autoencoders. Now, these are more about learning the structure of data, right? They compress images into a latent space and then reconstruct them later on. They are also useful for generating new images and understanding patterns in data. Now you have the fourth one, which is rapidly growing, and a lot of hype have been going around it. This market is rapidly expanding. I think about 38 billion expected. It is expected to expand by 38 billion by, I think, 2030 something. Yeah. So vision transformers basically look at global relationships right from the start. Now, as you go further, like when Alhaji is explaining how convolutional neural networks work, you will learn that like it detects local edges. But for this one, like it's gonna be it focuses on more on how one part of the image relates to another. I mean, like, which means they are very good at capturing global context, right? So I want to compare this. Okay, let's just do this. So the comparison for this for CNNs we discussed as number one is that CNNs are excellent when it comes to learning local features, right, like edges and textures. But vision transformers focus more on global relationships across the entire image. So in practice today, CNNs are still very efficient and widely used, but vision transformers perform extremely well on large data sets. And many modern systems combine ideas from both. But for a good start, as someone getting started, it makes sense to start with CNN or convolutional neural networks. So the next one is vision language models, which is the last one. And in summary, like vision language models allow systems to understand images using natural language, right? So for example, you can describe an image and then expect it to answer questions based on it. So next, we're gonna move on to some of the tasks for computer vision, right? Like some of the tasks that computer vision tasks are applied on. So you kind of have like object detection. So there are a bunch of them here. So you have object detection, and what this does is it basically identifies what objects are present and where they are in an image using bounding boxes. You have image segmentation, and this is, as the name implies, like it basically divides an image into pixel level regions. And this will allow precise understanding of the object and boundaries. You also have edge detection. This detects boundaries and sharp changes in an image, right? So it's often used as a low-level vision task to detect boundaries. You also have face and pattern recognition. And as the name also implies, it attempts to identify or verify who a person is based on facial or body features. And you have the one that is mentioned first here, which is video motion analysis. And basically, it analyzes movement over time in video to track objects or understand actions based on the context going on in the video. You also have image restoration. So, like, basically, it's just attempting to improve image quality. So this will mean that it will try to remove some noises, let's say like a blur image or distortion in an image. And you have the last one, which is matching and scene reconstruction. And what this is trying to do, essentially, it's going to match features across images to construct 3D scenes or understand camera movement. So now let's move on to the next slide. Now, one common question that you will realize as we are going on is going to be, why is computer vision hard, right? And it does make sense to ask this question, because what you will realize is that, like, for humans, like, we understand images naturally, right? Looking at this, I can tell a dog, I can tell it's a dog. But for a computer, an image is just numbers. And as we go further, you will see why this numbers is gonna be complex for the computer to understand. So moving on to the next slide. So the problem now, we can say an image has thousands of numbers, right? So I mean, like the question is gonna be now, how does a computer understand which of those numbers matters? Like as you can see on the right side, which is the visual, assuming that this is the visual view of what the computer is gonna see, comparing it to the left side. I am a human seeing the image. I'm obviously gonna know that this is a dog, right? But then for the computer, it's only gonna see numbers. And the question is going to be, how does a computer know like which of those numbers matters, right? Because not all of those numbers are useful, and not all of those numbers are going to be passed on to the next layers. So let's see, how does a computer know what matters? Now, before that, I mean, we should first try to identify what is our goal today. So we basically try to understand how CNNs help computers to do two things so far and right now. So first is trying to understand how CNNs can help the computer find important patterns, and then two, we're trying to see how can it ignore unnecessary details. If we say that we're gonna find important patterns, then it conversely means that there's also patterns and details that are not useful. So how do we make sure we ignore them? Now, let's just move on to the next slide. So there are two concepts that's very important to understand, right, before touching on CNNs. So first is the concept of images, and what type of images do we have in deep learning and when dealing with computer vision related tasks. So first we have something called a pixel, right? So like basically now a pixel is just a value, and then the image is just the grid of tiny squares, as you can see on the right. Now, once these two samples of dog is passed onto our computer, it's gonna be a tensor value. And once you print this tensor value using whatever framework you're using, what you will see is gonna be like this grid of tiny squares of numbers, right, ranging from 0 to 255. Now, let's move on to the next slide. So that's one, but then there are also two things, as I mentioned, that is very important. We have different kind of images, right? We deal with different kind of image data when it comes to trying to make the computer understand which of these numbers are necessary. So first we have something called black and white images, and it's also sometimes referred to as grayscale images, right? So a black and white image is really just numbers, and each tiny square you see in this pixel here, like on the image on the top, like each of those pixels has one value, and that value represents like how bright it is. So 0 means completely dark, and 255 means completely bright. And everything between 0 and 255 is just different shades of gray, like depending on how close it is to 0 or 255. And what will happen is that CNN or convolutional neural networks will work directly with these numbers, not the image we see. It will actually gonna work with these numbers, which are automatically translated as you pass on your image data. Now, from these values, from the image data, it's gonna start doing something called fuse extraction. Like it's gonna start to detect edges, shapes, and patterns. And there's a whole process on it, and Alhaji is gonna explain that later on. So basically, in the grayscale image, the computer sees the image like as a grid of brightness values. Now let's move on to conversely something called the color images, right, or RGB images. So in RGB images, as we mentioned in grayscale images, in RGB, like colors are basically, I mean, it's basically just like the same as grayscale, but it's just with some added information. So instead of one number, like per pixel, as we previously see, now each pixel you see here has 3 values. Now for the meantime, just forget about the 5 by 5, you will come to it. So for example, now, like one it's gonna be for red, one for green, and one for blue, right? And you can think of it as like 3 grayscale images stacked on top of each other, but then like with different values for red, blue, and green. And the combination of these three values is what gives us the final color we see. Now, one thing to elaborate on, like when I say color images, it doesn't mean that CNN is going to see a colorful card, like in this case. Like it just means that they see three matrices of numbers, like instead of cards, right? And then all the learning still happens on those numbers. And as you can see, like the 5 by 5 by 3. So this is basically like the height, the width, and then the number of color channels you have. So once this card image is passed, now we're gonna have three channels as we see here: red, green, and blue. And then for this case, now here is not going to be a 5 by 5 by 3. Instead, it's going to be a 4 by 4 by 3, because the height you have 4, and then the pixel values for the width is also 4. And the number of channels for the colors, like we have 3 channels, that translates to 3. So this is going to be 4 by 4 by 3. And this one, the one on the right is obviously going to be a different thing, right? So most likely this is going to be, I guess, around 13. So it's going to be 13 by 13 by 3. So essentially, that's how it works, right? Now, let's move on to the next slide. Okay, so now, why images are hard? As we are going through this, at first you'll be like, okay, grayscale images seems easy, but then once I start talking about the color images, you realize that, you know what, like this is getting too complex, right? And then that is just one image. And imagine we're gonna have, like, let's say you have thousands and thousands of data sets, and for each of those, it's gonna be the same scenario, right? Now, we will run into some problems, and one of the problems we run into is that there will be too many numbers. So, like as you can see on the grid, like the grid on the right, the image on the right is being translated into this. An image, like the image here, is basically just a massive collection of numerical values, pixel intensities. So in this case, you didn't see even the background of how the cat or Abraham Lincoln might look like. This is essentially how an image is going to look like, right? But then a simple image literally can contain millions and thousands of these numbers, which is going to make it difficult for humans, like, to program specific rules for every scenario. That's why traditional programming cannot even work in this scenario. And then second is going to be that, like, patterns are not obvious, right? So I might have two different kind of looking cards, but then the way their matrices is going to be completely different. So, like, the patterns are not obvious. The numbers alone don't immediately, like, reveal what the image is also. And then when a human sees a card, like, a computer initially just sees it as a vast array of numbers. And then, like, the patterns that form the card are too complex to manually define. So we might say, okay, there has to be a smarter way to kind of do this. Now, we can say, okay, we can say no rule guessing, no rules, no guessing, and learning from data. But if we have to look at this objectively, as in contrast to what we just described, if we say that there should be no rules, then it means we cannot write, like, a specific rule for every single object or pattern. So imagine we can literally say we'll have millions of different patterns, and there is no one who can sit and do all that. And second, if we look at no guessing also objectively, we will come to the same conclusion that the system cannot rely on random chance to guess what's in the image, right? Like, a doctor cannot rely on random chance for, like, a CT scan model to just give whatsoever prediction it gave. That's literally someone's life you're playing with. So now it means there's one which is basically learning from data, and let's see how this is gonna go. So for that, like, the modern approach will involve now feeding vast amounts of label image data into algorithms like neural networks, and then the computer then learns to identify these complex numerical patterns itself through exposure and patterns. So this transition from explicit rules, like, to this concept of AI, deep learning, computer vision, is the foundation of modern artificial intelligence. And from here, Al-Haji is gonna go ahead and explain more on, like, convolutional neural networks. Also,
thank you very much, Charna. I'll just get started here. So one thing I also want to mention is that like some of these matrices here is just used to illustrate. It doesn't mean the lengths, the sizes of the matrices are right. It's just to illustrate how things look like. So let's get started for convolutional neural network. So here's a diagram, but we're not going to go into detail about everything in the convolutional neural network, but I just want you guys to understand what is the input and what each convolutional layer is doing. And one more thing that is max pooling, then the output. So we can define convolutional neural network as an artificial neural network, as we discussed last week, 2 weeks ago. Which is primarily designed to extract features from grid-like matrices datasets, that is our image, and are so far most popularly used for image analysis. So like people always think convolutional neural network can is only used for image analysis, but like it can be used for other stuff because it is used to detect local features and not global as compared to vision transformer. So importance of it, as Chandra mentioned, this is the backbone for computer visions. It was first introduced in the early I think 2010, 2013, by Jan LeCun. It was used on the MNIST dataset to recognize handwritten digits, and it since have been popular, and it's used in facial recognition, image classification, and object detection. So our taxi in computer vision is we can do classification. We can do other stuff, but I want to talk about classification. For example, we have this image here of Abraham Lincoln, which is one of the four founding fathers of the United States. And as Gemma mentioned, an image is just a pixel of value. So we have a grid, a matrix grid here, so in all the pixel intensities of each pixels, and we can use our convolutional neural network to do classification. For example, we can classify whether this person here is Abraham Lincoln, George Washington, Thomas Jefferson, or Barack Obama. But how do we actually go from these numbers to this prediction? And that's what I'm gonna try to explain to you guys in a high level. So feel free if you have any questions along the way, just put it in the chat here, and we're gonna answer your questions later. All right, so here I have two images. The one on the left is Abraham Lincoln, and the one on the right is Barack Obama. Naturally, we humans know, and if I don't know, if you guys have seen Barack Obama, like you will know this person is Barack Obama. But how do you actually know this is Barack Obama? We know this is Barack Obama because of the features of Barack Obama. Let's say the hair, the eyes, the nose, the mouth, and the ears. Like if we put all of this together, we can conclude that okay, this person is Barack Obama. Even if we change the color of the image or we add filters to it, let's say we plot the image, we will still be able to know that this is Barack Obama because we're able to recognize the features of Barack Obama. Just like this one, Abraham Lincoln. Like what makes Abraham Lincoln Abraham Lincoln? It's because of the features of Abraham Lincoln. You know, the hair, the eyes, the nose, the ears, the mouth, and the beard, and so on. These are high level features, but I'm going to concentrate more on low level features like edges, lines, and so on. So for us to know that this is Barack Obama, we need to find features that make Barack Obama Barack Obama. For example, this one, the same, like the eyes, the nose, as I mentioned. So this process is called feature extraction. We're able to extract these features from the image and conclude that this person is Barack Obama or this person is Abraham Lincoln. So the same way we have to teach our computer like that, for it to recognize these features and know that, okay, for me to recognize, let's say, a human from an image, okay, there must be a hair, there must be an eye, eyebrow, nose, ears. So these are the features that makes up a human. So the computers will be able to extract these features and know that if these features are present, then the output is this person is a human. Or if these specific features for Abraham Lincoln are present in this image, then the output is going to be, okay, this person is Abraham Lincoln. So as I mentioned, these were high level features. For example, for a human, you know, we have things that makes up a human: the nose, the eyes, the mouth. And for vehicle, we have the wheels, the license plates, and the headlights. And for like a house or mansion, we have the doors, the windows, and steps. So like if we're trying to program a computer to be able to detect or classify an image as a house, it should be able, the things it is going to be looking for are these features: the doors, the windows, and the roofs, the steps, and other items. So those were the high level features, but we have very low level features like the edges, the dark spots, the lines on images and features. Then we have the mid level features like the nose, the ears, and the eyes. Then we have the high level features like facial structures. So we start from identifying the edges, then going to high mid level features, then going to high level features. So just like the way humans learn, from low to high, that's how we're going to teach the computer. So, but I want to introduce this key term here: filters or kernels. This is I talked about feature extraction, like knowing that this is what makes up this item. So let's go look for those items in the image, and we're using our filters to do that for us. So a filter is a tiny window that slides across an image and looks for a specific pattern. So it is also a matrix. So you get the size, you define the size. So here we have a 5 by 5 filter, and it is used as a tiny window that's going to slide across our image and looks for this specific pattern. So let's say like a horizontal line in an image. So we're going to have a filter which can identify horizontal line. Then we pass that filter across our image to look for horizontal lines. So to think about a filter, right? Let's say we have this scenario. We all have seen this in movies. So let's say the filter, like there's a crime scene, right? The filter is the detective, and the crime scene, the image is the crime scene. So what the detective does, it moves around room by room. So for our case, pixel by pixel, looking for clues without which are the patterns, the features we're looking for. When it finds the patterns, it recognizes it and it raises a high signal. So like our filter is going to go through our image. Let's say we are looking for a horizontal line. If it sees a horizontal line, it's going to have a high signal in those areas where it thinks there's a horizontal line. So we're going to see how this actually works. So this is called a convolution. So the name convolutional neural network, the word convolution comes from this part. The process of us using a filter and going across the image and looking for those features or detect items that we are looking for in that particular image. So this process is called convolution. And the output of a convolution of us using a filter and straddling it across our image. So an example of filtering is like edge detection. Like we can have this image, then we have our filter which can detect edges. So we pass it through the image to detect all the edges in that image. For example, the image on the left, we have the image on the left after we applied the filtering, the edge detection filtering, then we have the image on the right. And as you can see here, the image on the right is only going to return the image where it finds all the edges. So we can see the edges of the person here, the person playing at the back, and the trees and the roofs and the houses. So it was able to detect all the edges, most of the edges in that image. So this is what the process of convolution happened. But we don't only use one filter, it uses many filters. So, but before extracting features, the CNN needs to learn what feature matters. Before we say, okay, we want you to detect this person, let's say Barack Obama. First, it needs to know what Barack Obama looks like, right? And traditionally, we have hand design filters. This is the old way. So we have filters like vertical filters, horizontal filters. Before in computer vision, before deep learning, like they use filters like the Sabo, the Kani, and the Gabo filters, which are used to find and extract these items like horizontal line and vertical lines and edges. So we define these detectors and we define the corner detectors. But because this is deep learning, we can't go, let's say we have millions of images, right? We can go through, we can hand design all of these filters to identify each of those items we're looking for. And since it's because of deep learning, the CNN learns its own edge detector. So we don't tell it this is how this an edge look like, or this is how an ear look like, or this is how other features look like. They often end up looking similar to Subble and Gabo, which are discussed like the hand digit, but nobody programs them manually. It's able to detect the edges, the textures, the shapes, the objects, and the full object and the full objects at whole. So instead of us manually defining that this is how an edge look like, this is what a texture is, this is what a shape is, it will be able to detect all of that without us manually telling it to. So 2 weeks ago, I talked about the neural network, right? After our forward pass, we calculate the difference, and this is our loss function. This tells us how close we are to the right prediction. So, and the smaller it is, the better it gets, right? But for our convolutional neural network, right, we after computing in the CNN, the filters are the trainable weights. They update through back propagation, just like any other neural network. That's how they learn what features to detect. So if you're wondering how these filters get better over time, since at the beginning it is randomly initialized, how does it know that this is what an edge is? So after we compute the loss function, it is passed back to the network through back propagation, and the weights of these filters are updated. So after the first byte, it makes an error. We update the filter. We go again the second pass. We calculate the error. Then we go back. We update the filter. So like the more we do this, the better the filters get at recognizing what they're supposed to do. So this was a process we discussed last week, and it is applicable here too. So let's visualize the process here. Let's say we have this filter, right, which is a 5x5, and we have our image. So what we're going to do is we're going to pass this filter starting from the top left corner, right? So let's say this filter is used to detect horizontal line. So we're going to find horizontal line in this spot here. So just like Cherno mentioned, like the local area instead of like the entire image. So we're just concentrating on a particular local area. So at this spot, we're trying to identify horizontal lines. Then we're going to move. When we are done identifying horizontal line, then we move one step. Then we can move again. We move, then we're gonna keep moving until we reach the end. Then we come back one row below. Then we do the same stuff again. We keep sliding, we keep sliding only until we reach the end. Then we go down again. So we keep going down, and then all the way we're gonna keep sliding until we reach the end. So at the end, this is gonna give us an image where it was able to detect horizontal lines from that image. So the sliding process, going around this image with our filters and moving it across the image is what gives us the convolutional neural network, their name. So the convolutional neural network, it's a neural network with convolutional layers which contains filters used to detect features from an image by sliding those filters across the image multiple times. So that's basically how it actually works. So we can modify our definition and say a CNN is a type of deep learning model designed to automatically learn patterns from images by using filters that scan over the image to detect features like edges, textures, shapes, and objects. So, but what actually happens when we slide over each of those tiles? So it calculates the dot product. So the convol filter with the image that is sliding over the image spatially, we're computing the dot product. And if you have taken mathematics, you might uh, have encountered this dot product. So basically what the dot product is, let's say we have this image patch here, right, which is a 3 by 3, and we are applying a filter, which is a 3 by 3. All it does, it multiplies each of those and gives us the sum. So here we start at the top, we have 45, right? 45 times 0, then we get 0, plus 12 times -1, -12, plus 5 times 0 is 0. Then we do it the same for the rest, and the summation of that is going to be -25. So this is going to give us the dot product. So this entire part here, this entire thing here is now represented only by minus 45. So this is what is happening anytime we're using the filter across the image. This is important because it it awards high numbers. So like if there's a high signal, the value goes higher, and it also, if it's a low signal, it goes lower, because we don't, the low signals don't tell us that there's a feature here, like it's a very low signal, so it's going to get rid of those, and also the image is going to get smaller, and we're only going to concentrate on where the features are actually. Then this process that happen multiple times, as I mentioned, like, we keep sliding and we keep calculating the dot product. So the more, every time we slide, the image get smaller. So here we have we have a 6 by 6. Now the output is going to be just a 4 by 4. So like the more we go, the more we shrink the image, and we are only focusing on the important signals. All right, so just like humans, right? We learn, as I mentioned, we learn step by step. So this is an example of how a convolutional neural network actually learns. So let's say we have an image here, and the first hidden layer is going to have multiple filters, and we're going to detect edges. Then let's say the second hidden layer is going to be detecting mid-level features like eyes, nose, hairs, and the third hidden layer is going to be able to detect let's say facial features, like this is a face, this is a hand, or this is a leg. So it gradually understand the entire image by breaking it down from lower level to mid level to high level features. But why the image is still large, right? And same patterns appears many times. There's a small shift in position, and the processing, everything is very slow. Like convolutional neural network is computationally expensive. So do we really need all of this number? So let's say this was the heat map, right? After we inputted the image into our model, after the first layer, we have something like this. And here, as you can see, the red shows us the important features where it thinks the features exist. So it means that all this blue here, we can get rid of the blue and we can save some computation, and we can only concentrate on areas where we think these features actually are. So one way we can do that is through max pooling. So let's say after applying our feature, we have this 4 by 4 matrix here, and we can apply a max pool. So let's say we have a 2 by 2 max pool. So we divide this into 4 areas. And what max pooling does, it goes into each of these smaller matrices and only takes the maximum number from each of those. So here we have 2, 2, 4, 9. So it's going to take the maximum number and represent this entire 2 by 2 grid by only 9. So we come to the next one here. We have 7, 3, 6, 1. So the maximum value here is 7. So it's representing this entire 2 by 2 matrix with 7. So we do the same for the other smaller matrices. So here we have 8 and we have 6. So this now reduces our image from a 4 by 4 to just 2 by 2. And we are only concentrating on the high signal values. So here we have 9 because it's the one that shows us the highest signal, 8, 6, and 7. So like the image is smaller, it is easier for us to process, it is computationally inexpensive, and we're only concentrating on the features that actually matters. So this is the idea of max pooling. So we can see from this image here, we apply our filter, then we have minus 45, 12, 22, and 10. Then after applying max pooling, we take the maximum, which is 22. So like we're shrinking the image very much, but like we're not losing important signals because we're only getting rid of signals that are not important. So this entire block here after applying the filter is now only represented by 22. So this is the example of a complete neural network. So we have a complete convolutional neural network. So here we have our first image, our input here. Then we apply a filter to it. Then we have our output here. Then we do max pooling. Then we have 22. But it's not only going to be one number. So these are just use a subset of the matrix here. But it's going to be like different, a lot of numbers here. Then we pass it through the network. Then it's gonna go through the other layers. Then after that, it's gonna go through the the hidden layers. Then at the end, it's gonna flatten the image, and it's gonna compress it and do comparison, and it's gonna give us what it thinks this image is. So here it is thinking that this image is 80%. It is 80% sure that it is Abraham Lincoln. 10% sure it's George Washington. 4% sure that it is Thomas Jefferson, and 1% sure that it is Barack Obama. So it was able to predict that this person is Abraham Lincoln by 80%. So that's basically how a convolutional neural network actually works. So using this matrix here and applying filters to it, then we have our output. Applying the filters, it calculates the dot product between this and the blue area here. Then we compute, then we use that dot product, the output of the dot product after applying it to the entire image. Then we calculate we use max pooling. Then we do that multiple times until we get the right prediction. So this is just like a high level overview, and this is the core idea. If you understand this, you're good to go. But there are other things too that go on, but like this is the main idea you have to understand. So it makes the prediction 80% that this is Abraham Lincoln. So let's do a demo here, and the demo I have for you guys today is it's a YOLO model. So it is a computer vision model used. It is the most popular used computer vision model, and it is used for tasks like object detection, defect detection, and other stuff. Let me share my screen here. All right, so okay, so this is the file for the training. And here all I'm doing is I don't even need torch here. Here all I'm doing is I'm importing the model, which is I'm using the library Alterytics, which hosts the YOLO model. So from Alterytics, we're importing YOLO because that's what we want to use. Then for our model, I'm using YOLO V8. It's early on this line. Then here is we're training our model, and this is entire. So instead of us manually building the neural network, the convolutional neural network, this library does everything for us. So all we have to do is call the train and pass in the parameters. So these parameters for the data here, I have a config file, so I can show you guys what the config file looks like. Okay, so this is the config file. It's showing us the part where the data can be found here. Then for the training, I'm using the images folder where I'm using the training here, which is in the images folder. And for the validation, I'm using the validation, all the images in the validation folder that is in the image. So you can see that I have the images here, but like I separate them into training and validation. So next week we're going to talk about memorization and generalization, because if we train our model on our data, right? We want to test it whether it's going to work on other type of data. Let's say we train our model to identify what a bottle is, right? And I have like 100 bottles. So instead of training it on 100 bottles, it's going to memorize all of those 100 bottles, and it's going to give us, every time we try to predict, it's going to be able to give us the right prediction. But let's say I have a different bottle which is slightly different from this one, then it might struggle to identify it because it has never seen that. So that's why we split our data into training and validation. So usually it's 80-20 split. So 80% of the data will be used to training. Then after training, we test our model on the rest of the 20% to see whether it's correct. So here it's going to give us like the count, like, because this is a classification, we only have two, which is where 0 means this item is intact and 1 means the item is damaged. So let me show you how the data actually looks like. So here we can see we have images here, training and validation. So this is a sample of the image here. So we have an image here of canteens, where we have 1, 2, 3, 4. We have 12 images, 12 objects in this image. So we can see that this one right here has a defect, and this one right here also have a defect. So we're training the model, and the way we're training it is like, we don't only use this image, we don't only pass this image, we have to tell it that where the defect is, and so that it learns what a defect looks like. That's why here in our data folder here, um I have the images, then I have the labels. So if I go to training here, each image have a label. So if you look at this label here, it's just these matrices, and the 0 tells us whether. So we have this image, right? There is 12 of them, and if we go here, we have 12 of them, 12 objects. So it's gonna look at each of those objects and say, okay, the first one is 0, which means it is intact, right? It is not a defect. Then it goes to the second one. Okay, it is intact, it's not a defect. Then it's go to the third one here. It says that, okay, this one has a defect. Then it goes to the last one here, which has a defect. Then we can see it here that the 1 means it has a defect. So the 0.203 shows us the X center, like from the horizontal line, and the 0.2125 shows us the Y center from the vertical line. And this one shows us the width, and this one tells us the height. So what YOLO actually does, it draws boundary boxes here. Let's say for this one, it draws a box around this. So like those width is telling us the width of this object, and the height, and then the X center and the Y center. So like it's using these labels to calibrate where these objects are, and telling the model what this object actually is, whether it is a defect or it's not a defect. So this is called supervised machine learning, because we're showing the model what the objects look like, so that it can improve from those, the more training we do. Okay, so now we understand what the data looks like. So we always need to have the image, and we also need to have the object. And for the image, we need to split it into training and testing. So going back to our training script here, so I will try to explain each of these parameters. So the data here is the YAML file, which is the config file I just described here. Then we have the epoch. So the epoch is the number of trainings we do. So think of it as the first time we pass the entire data into the network, that's one epoch, right? Then we pass the data again, that's another epoch. We pass it again, that's another epoch. So it specifies the number of times we want to pass the data across the network. So here I'm choosing 300 because I'm training this on a GPU. It's really quick to train this on 300 epoch. But like if you want to do it on your computer, it's gonna take hours to train this. And I think I'm gonna share this um files and folders. You guys might try to run it on your laptop, but it's better to start with a small number. Let's say like 1 epoch, 2 epoch, or 3 epoch. So I'm specifying here the image size is 640 and the batch sizes. So instead of passing the entire image once through the network, I'm using batches. So I'm just passing 32 from the data, then another 32, then another 32, and then another 32. So instead of passing the entire image into the network, I'm passing it like by batches. Then here it's specifying the name of the experiment. The patient here is 50, like it specifies the early stopping patients. So what this actually does is like let's say we're training the model, right? And the accuracy, or I mean, on this case, it's not using accuracy, but let's say the metrics is like all of them are at 90. Okay, it's 90, 90, but we see that it's not improving, then we're gonna stop the training. Then if we did not stop the training, it's gonna overfit, it's just gonna memorize the data. And if we give it new data, it's like a data it has never seen, then it's gonna perform poorly. Then I'm saving the checkpoints here, which are the weights of the model, and after each training. Then the plots, I'm not doing plots because it makes the training faster. Then the other important one here is the optimizers. There are like different type of optimizers. This is where we do the gradient descent, as I explained last 2 weeks. So I'm using Adams, but you can use others like SGD, the learning rate, the weight decay, and the order. So here I'm just printing the output. So let's see what this actually look like. So after training this for 300 epochs, so we can see that like after 150 153 epoch, it stopped because like there wasn't a lot of improvement going on. We can see that 2599, 2595. So it's like in that range. So 0.30, 0.30, 0.30, 0.81, 81, 82. Yeah, so it wasn't a lot of improvement going. So like so it says there was an early stopping, the training stopped early as no improvement observed in the last 50 epoch. So in the last 50 trainings from 103 to 153, there wasn't a significant improvement. So like we have to stop the training because the more we continue keeping training, the more it's not learning, it's just memorizing, So like we need to stop training. So the best result was saved here. And here we can see that we had 34 images for all of them. And we have the instances is like 380. So like in all of those images, we have 380 objects in those images. And 207 of those were intact and 174 of those were damaged. So this is the validation results here. We have MAP 40, 0.98, 0.92, the precision is 0.93, and the recall is 0.95. This is actually very, very good, right? So this is a very good result here. And we don't have accuracy in this. And in 2 weeks, I'll explain why YOLO model does not use accuracy, because like accuracy is also very misleading. It's not a good metric to determine whether our model is performing well or not. So in the next 2 weeks, we will talk about how accuracy is also not a good metric. So like it uses precision and recall, which are really, really good. And for my case, and most people say like it's way better than accuracy. All right, so after training this, we have the runs here, and this is it here. It stores all of these values, and these are the weights here. Last week, last 2 weeks, I explained the importance of weight. The weights are the models. It's what the model learned. So after the training, it is frozen, and we have them here. So I asked thought the best one after all of the training we did. Which one was the best? Which of the training was the best? So like we stored the best model, and this was the last one, but I'll be using the best model to do the prediction. So if we come here, I have I have a small script here where inference that in this notebook here. So all I'm doing here is I import alternatives to use the model. So here, the model I'm using, you remember when here I used YOLO, I used YOLO something, YOLO V8. But here, instead of using that model, I'm using the model we trained, now we're able to train our own models and we have the weights and I'm using the best weight. So now I want to predict whether this image P1 P1 JPEG. Let's see how this image actually looks like. So this was the first image we saw. So the model should be able to predict that. Okay, the third one here is has a defect, and this one here to have a defect, but like all the rest is intact. So we're trying to see whether the model we train will be good at doing this. So we have this, then we uh we we get the image, but like the image is BGR because that's how OpenCV stores it. So like we have to convert it to a RGB. We've discussed RGB before, and if we run this, this is actually what I have here. So it is 92% sure that this object is intact. It is 95% sure this one is intact. 96% sure that this was a damage, and 95% sure that this was a damage. So it was able to identify all of them with high confidence. So like our predictions were correct, and it gave us very high confidence. So that's everything here, and I will share all of this code and you guys can try it out. So that's the end of the demo, and we will answer some questions, and Cherno, if you have anything to say.
So yeah, thank you so much, Alhaji. This was very, very impressive. If you guys have any question, feel free to drop it in the chat or unmute yourself and ask. So yeah, feel free. And one thing to also announce, so our next meeting will be next 2 weeks. That will be next 2 Saturdays, right? So we will send updates in the group chat. So you can stay connected there. And Alhaji will also share these codes for you guys to try out. This is actually very, very impressive. I also have some notes. Probably I will be sending them there. But for now, if you have any question, feel free to ask or drop it in the chat and we will answer it. Yeah, if there are no questions, I guess we can call it a day. Then we meet next 2 weeks.
All right, thank you guys for joining. See you guys in 2 weeks.
Yeah, see you guys in 2 weeks. Bye.